Part of the disclaimer, the views and opinions here are only those of the presenter and don't necessarily represent the opinions of MRMC or the Army. I'm a representative from CDMRP. It's a congressionally directed medical research program. So we fund a lot of the medical devices from cancer research to prosthetics research. My background is in biomedical engineering, so I manage a lot of prosthetics projects. I'm the science officer within the Orthotics and Prosthetics Outcomes Research Program. So it's a congressional program that was started in 2004. The vision and mission statement are on the slide, but basically we fund a lot of the devices. We do a lot of the research that makes sure these devices actually work and are impacting our warfighters. We do a lot of extramural funding, and so actually I would like to introduce Mr. Blair Locke from COAPT Engineering, and he'll talk you through the technology.
It's a pleasure to be here. I also would like to introduce Glenn, who we'll have the pleasure to hear from in just a moment. I'd just like to take a minute to explain the technology, what it is, really what Glenn is wearing today. So here we are in 2017. We have really capable humans, and by that I mean amputees, so people that have been injured in battle or in their own daily life. And these are people that have the ability to lead a normal life. We also have capable prosthetics. These are highly advanced, well-developed robotic technologies. Funding has gone into these. These devices work really, really well. One of the challenges we have is how do you make the connection? So what is that human-machine interface? We can have really good control from the mind of that individual, and we can have really technology that is really capable. And how do we connect those? Neural prosthetics or neural prostheses comes up a lot. So how are we going to make that neural connection to that prosthetic device really effective? There is something that we lean on a lot. The fact of the matter is that human nerves, our nervous system of our body, is an electrical system. It carries information electrically that is the intention to move one of these devices. The problem is, typically, these nerve signals are too small to be recorded in a day-to-day activity-like situation. They require invasive technology to record them. They work really well in the lab, but as soon as we move outside in the home or in the field, they break down. They're not as reliable. So we have a little bit of a solution at our hands. Muscles in our body can act like amplifiers of the nervous signal, the nervous system's signals. Just like a speaker might amplify the information in the speaker wire, our muscles will amplify the signals from the nerves of the body. So how do we put that in play? Well, it's something we call pattern recognition myoelectric control. Myoelectric, if that word is new to you, means muscle contractions. Any muscle contraction we make in our body emits electrical activity. This is myoelectric. Each time that any of us with intact limbs or amputees like Glenn intend to make a hand and arm motion, they make different muscle contractions, and those make a repeatable myoelectric pattern of information that can be detected. So in a prosthetic device, what we do is we create an array of non-invasive electrodes, and these sit on the surface of the skin of somebody like Glenn, and we can detect those patterns. Using real-time algorithms, machine learning, whatever fancy word we want to put to that, we can decode that neurological information to permit intuitive prosthesis control. As you might imagine, that provides great benefits, not to just the user, but to the clinicians who are fitting these users, making the process more efficient and more functional. This technology has been commercialized with great help from lots of partners in about 2013, but it's not new. It's been under development for about 50 years, started with some naval research in the 1960s. Since then, the research and development has really led us to what we can see today on the commercial market. At COAPT, we do provide this as a commercial device. Now, we don't make the parts and pieces you can see. We don't make the hands, the elbows, the wrist units. We make the control system, so the brain of the system. We sell it as a pattern recognition add-on kit. It fits with all the major manufacturers of prosthetic devices on the market. It is an artificial intelligence system, which means it can be learned and it is taught. So it learns Glenn. The more he wears it, the better this system gets at listening and being functional for him. It provides that level of intuitive and superior control, and it leads to a better daily life for Glenn. This has been something that's been provided throughout the U.S. since 2013 to a lot of our wounded warriors. So I'll finish out by saying, what are some of the key benefits of this pattern recognition? Well, it's a significant advancement over the incumbent style of how amputees would control prosthetic limbs. It has a lot of things that we can add to it, like virtual and game-based training that really help out in clinic and make these individuals adapt to their devices and devices adapt to them rather quickly. We have a calibration feature, which is not normal in prosthetics, and this lets Glenn individualize and personalize it through that machine learning to make this system one with himself. And it is a complementary technology. In our small field, we often get mistaken for this is a replacement to some other surgical technique or something, which is not true. So osseointegration, which is the practice of physically connecting a prosthetic to a human via a titanium implant, for example. Other surgical techniques, targeted muscle reinnervation, this is complementary to those. So with that, I'll let Glenn talk here. Glenn is a transhumeral amputee. He's been a recipient of something called targeted muscle reinnervation surgery, which allows him to control these very well. He is wearing a power actuated elbow, wrist, and hand, and he has a co-op system that he can tell you all about.
Hi, good afternoon. My name's Glen Layman. I'm a retired Sergeant First Class from the United States Army. I lost my arm in November of 2008, and I was treated here locally at Walter Reed. Being a new amputee, I had to go through a lot of training. For prosthetics. You have to learn and develop control. With traditional prosthetic devices, the control is you have to be able to trigger and hit a switch, kind of like at the circus, where you slam the hammer down and the thing goes up and it rings the bell. So you have to ring the bell to get the motor to move every time. So you can see how tiring this can be for somebody that just lost a limb and are trying to constantly keep flexing or using the muscle to reach this threshold through the day. Imagine equate it to doing CrossFit 8 hours a day. You know, at the end of the day, you're not going to be able to ring the bell. So it's very strenuous traditionally how you use a prosthetic arm. Also, you can only do 2 functions at one time. So you have to sequence through from elbow to wrist to hand, and then you have to go back through. So you have to get the arm sequentially controlled in a process or in your right position so that you can use it. With COAP, with our pattern recognition system, as long as you can replicate or create a pattern, the algorithm assigns it to a motor movement. I can retrain it as I get weaker through the day. So let's say I've been doing, pull-ups for 8 hours now. I can't quite get my chin over the bar anymore. I can retrain the threshold and I can bring the bar lower. So that way I don't have to go so far. It also reduces my dependency on a clinician because I can change the thresholds in the arm myself. I don't have to go back and make a doctor's appointment and see somebody to constantly keep adjusting my arm. I can kind of fine tune it myself. As I told you before, we had to sequence through elbow, wrist, or hand. What we have with pattern recognition is what we call seamless sequential control. So as you see, I was standing over here, I have access to all 3 motor movements in my arm at one time. I have an elbow, I have a wrist, and I have a hand. I can go right from elbow up to elbow down. I can open my hand, I can close the hand, I can pronate the wrist, I can supinate the wrist. Before, I would have to use some sort of switching mechanism, a co-contraction, which is extremely painful for an amputee to make, or some sort of linear transducer or something to change the motor function in the arm. Now I have access to all 3 of those movements independently. So people ask, what is the biggest difference with COAP and our pattern recognition? It's intuitive control. So the arm has learned me, how I talk to the arm. So it took where I had 6 months of training when I first lost my arm to be able to use a prosthetic. Now we can do that in 6 weeks. We can, as long as you can replicate the pattern, you can go through, our training process takes about 30 seconds. In about a half an hour, you can almost master it. So you see clinically how fast it is to get the patient from where they were dependent on other stuff to back to independence.
So thank you. We're going to keep that short. If there's any questions, we're going to be over at the booth just over here. I'm happy to chat with everybody. Thank you.